Hi everyone, welcome back to Z Physics. Today we are going to be talking about a very attractive topic, which is gravitational fields. This will be a revision lesson and I'm going to be following the specification as said by OCR Physics. However, if you're doing a different exam board as well, this video will also be applicable, but I would just make sure to check with the specification of your exam board to make sure that we've covered all the points. Okay, well, let's get started. Now, the first thing that we need to note is that gravitational fields are due to objects having mass. That means that any two objects which have mass, let's say that we have one object here, let's draw a sphere over here and then another sphere over here. Let's say that the one on the left has a mass m and this one here on the right has another mass m. They are going to experience an attractive force due to those objects having mass. Now, also throughout the gravitational fields topic in A-level physics, very often we model spheres as having all of their mass concentrated in a point mass at the center of the sphere. And we are going to be doing this in quite a few equations throughout this topic. We can also represent the gravitational field with gravitational field lines. Now, because the force is attractive, the field lines, they're just going to follow the direction that a little test mass will experience a force at, and in this case, that is towards the center of this planet. So the gravitational field lines are going to be radial, pointing towards the center. Also keep in mind that if there are twice as many field lines, the gravitational field will be twice as strong. In other words, the gravitational field strength is represented by the density of the field lines. Additionally, as we know, the formula for gravitational field strength is that G is equal to the gravitational force divided by the mass m. So we could measure this in newtons per kilogram. So n kg to the power of -1. As you also know, we could also measure it in meters per second squared. Now let's look into more detail into the nature of this force F. This is Newton's law of universal gravitational attraction, and if we have any two objects that have mass, for instance, one of them has a mass lowercase m, another one has a mass capital M, the force of attraction between them will be acting on both of those bodies, and it's an attractive force. The equation for it is that the gravitational force is equal to minus g times the product of the two masses divided by the square of the distance between those two objects. And second law says that the net force acting on an object with constant mass is essentially equal to ma. We can set this left-hand side of the equation equal to ma, and this will be equal to minus gmm over r squared. Notice that those two m's are going to cancel, and we are left with an expression for gravitational acceleration, which is minus gm over r squared. Now, because this is gravitational acceleration, often we don't call it a, but we just give it the letter g. And this over here is the formula for gravitational acceleration. Please remember that gravitational acceleration is one way of measuring the gravitational field strength, and this formula over here really is a formula for the gravitational field strength. Additionally, the gravitational field strength can be approximated as being uniform close to the surface of the Earth. If that's the case, the field is also uniform, and the way we represent this is with parallel lines that always enter the surface at 90 degrees that are equidistant. That means that the distance between them is absolutely constant. If the field was stronger, we would just add some more lines, just like this, which is an example of a stronger gravitational field. Remember, gravitational fields is what's actually keeping the planets in orbit. So let's have a look at Kepler's 3 laws of planetary motion. Law number 1, the orbit of a planet is an ellipse with the sun at one of the foci. Kepler's second law says that a line segment joining the sun and the planet will sweep out equal areas in equal times. Now imagine the planet goes from point 1 to point 2 in its orbit in, let's say, 1 month. So this distance over here is being traversed in a month. Now let's say that the planet goes from 3 to 4 in also 1 month. Those two areas are going to be exactly the same. So area A is going to equal to area B. Now this is actually a consequence of the fact that the planet is speeding up if it's closer to the sun due to the fact that it's experiencing a higher gravitational force. Now Kepler's third law is that the square of the orbital period of a planet is proportional to the cube of its orbital distance. Mathematically, we could express that as t squared is proportional to r cubed, like so. Of course, we could also write that t squared is equal to some constant k multiplied by r cubed. We're going to prove in a second what the value of that constant is, but more importantly, we know that t squared divided by r cubed will be equal to some constant k, and mathematically we can always write this as t1 squared over r1 cubed, which will equal to t2 squared over r2 cubed. And this can be particularly useful for some problems in which essentially we'll be dealing with proportionality between either of those quantities. Let's prove Kepler's third law. The way we start this derivation is by essentially remembering that the gravitational force is acting towards the center of rotation of the planet. This means that we can set the gravitational force Fg equal to the centripetal force, which in this case I've just called F subscript c. The magnitude of the gravitational force is equal to gmm divided by r squared, and if you remember from circular motion, our centripetal force is equal to mv squared divided by r. I'm just going to cancel those m's over here, and additionally I'm going to remember that whenever we have an object moving in a circle, the speed v will be equal to the circumference of the circle, which is 2 pi r divided by the period of rotation, which in this case is just equal to t. Now what I'm going to do on the side here is just square this. So I'm going to go v squared is equal to 4 pi squared r squared divided by t squared. Then what I'm going to do is I'm just going to sub this into this equation. What I'm going to be left with is that gm divided by r squared will be equal to, well, rather than v squared, I'm going to write 4 pi squared r squared, and then I'm going to be dividing by r t squared. Notice that in this case, this r is going to cancel out the square here, and all I need to do really is just do some rearranging. So I'm going to rearrange for t squared, and t squared like so. If I bring this over on this side, what I'm going to be left with is 4 pi squared. Then when I bring this factor of r squared over to the right hand side and multiply this by the leftover r, I'm going to have a factor of r cubed. And then finally, I need to bring gm on this side of the fraction, so I need to divide by gm. And there we have it. This is Kepler's third law. T squared is equal to 4 pi squared divided by gm multiplied by r cubed. Now let's speak about geostationary orbits. Remember there are a couple of defining characteristics of them. Number one, probably most importantly, they have an orbital period of 24 hours. That is, of course, in the same direction as the rotation of the Earth. Also, they are an equatorial orbit just above the equator. Because of these characteristics, 1 and 2, they remain fixed in the sky to an observer on Earth or to a satellite dish pointing at a specific location in the sky. Now let's calculate the height of a geostationary orbit, and the way we're going to calculate the height of a geostationary orbit is by using Kepler's third law. So I'm just going to write this over here. T squared is equal to 4 pi squared divided by gm r cubed. Now the orbital period is 24 hours, so what we need to do is find the distance r. Let's also just write down a couple of useful numbers for you guys to actually be able to solve this question. So the radius of the Earth is 6,400 kilometers, and the mass of the Earth is equal to approximately 6.0 times 10 to the power of 24 kilograms. Okay, well, let's calculate the height of a geosynchronous satellite above the surface of the Earth. So essentially we need to rearrange this equation for r cubed, and let's do this. So r cubed will be equal to t squared multiplied by gm divided by 4 pi squared, and what I need to do is take the cube root of this expression like so. Remember to actually press the cube root button on your calculator. Common mistake is to just press the square root button, and that'll be the cube root of t squared gm over 4 pi squared. Okay, well, let's plug in some numbers into this equation. So t squared, this will be actually 24 hours, so that's 24 hours, 60 minutes, 60 seconds each. Don't forget to square this, multiply by g, which is equal to 6.67 times 10 to the power of minus 11. The mass of the Earth is equal to 6.0 times 10 to the power of 24. Now what I'm going to do is divide this by 4 pi squared, like so. We're going to get approximately 4.23 multiplied by 10 to the power of 7 meters. Now notice that this is not actually the distance to the surface. Remember when we talked about point masses at the center of objects, that equation actually assumes that this over here is the distance from your geostationary satellite to the center. So I'm just going to write over here that this is the distance to the center of the Earth from the orbit. Now, in order to find the distance or the height above the surface, we need to take away the radius of the Earth. In other words, the distance which we have found is this one over here, and the one that we are looking for is this blue distance. Now this blue distance, which is the height, let's call it h, will be equal to 4.23 times 10 to the power of 7 minus the radius of the Earth, which is 6,400 kilometers, like so. So it's going to be 6,400 kilometers, so it's going to be times 10 to the power of 3 meters. And let's just put that into a calculator and take it away. So minus 6,400 times 10 to the power of 3, and that's going to give us about 3.6 times 10 to the power of 7 meters, which is the height of a geostationary orbit. Now next, let us once again summarize the three main equations in gravitational fields. First of all, the gravitational force is given by Newton's law of universal gravitational attraction, that the force F is equal to minus gmm over r squared. Gravitational potential energy, on the other hand, is expressed with this expression, minus gmm over r. Notice that this r is no longer squared. The gravitational potential, which is almost like gravitational voltage, is actually equal to minus gm over r. So the gravitational potential is simply the energy per unit mass, really. So it's the energy per unit mass. Notice that between the two formulae, there's only a factor of m missing. It's really important to note that both of these quantities are zero at infinite distances. So what actually happens is that they are negative and they increase up to 0 at infinity. So we should even write this down. So both the gravitational potential energy and the gravitational potential are they are negative and increase with distance. They're negative and increase with distance. For instance, if something is negative, it can increase. I can give you an example. We have minus 5, minus 4, minus 3, minus 2, minus 1, 0 at infinity. This is how it works with gravitational potential energy and the gravitational potential. They are negative numbers which start tending towards 0 as the distance tends towards infinity. This leads us to a very important definition for the gravitational potential. And remember the gravitational potential Vg, this is the work done required to bring a unit mass from infinity to the point. And we need to make sure that we remember this definition for our A-level physics exam. Now let's think a little bit more carefully about work done. If I have a graph with the force on the y-axis and distance on the x-axis, I can actually find my work done, because work done will be the area underneath the graph, underneath a curve in a force distance graph. And this is really important. That is because we generally tend to find the area by multiplying whatever's on the y-axis with whatever's on the x-axis in these tiny little squares, then add them all up and to get the entire area. And remember, work done is equal to force times distance. One final thing that we need to be talking about is escape velocity. Remember, there's a certain velocity that if it is reached, an object will leave the gravitational field, and this is known as the escape velocity. Now, in order to find the escape velocity, we need to be thinking about energy. So the way we do that is by setting our gravitational potential energy. Let's call that GPE. It has to equal to the kinetic energy. Let's call that KE. Now remember, the formula for gravitational potential energy is GMM over R. At least that's the magnitude of our GPE. This is going to equal to the our kinetic energy, which is a half mv squared. Now the m's are going to cancel, and we're just going to rearrange for v, which is our escape velocity, and v will be equal to the square root of 2gm divided by r. Now for the Earth, the mass of the Earth, remember, is equal to 6.0 times 10 to the power of 24 kilograms. The radius of the Earth is equal to 6,400 kilometers. So we can plug those numbers in and find the escape velocity of the Earth. So this will be equal to the square root of 2 times gravitational fields constant is 6.67 times 10 to the power of minus 11. My square root is not long enough. Multiplied by the mass of the Earth, which is 6.0 times 10 to the power of 24. Let's make sure we square root everything. Then we're going to be dividing this by the radius of the Earth, which is 6,400 kilometers. So that's times 10 to the power of 3. And if we put these numbers into a scientific calculator, we're going to get about 11 times 10 to the power of 3 meters per second. Well, that's about 11 kilometers per second, which is the escape velocity on Earth. Okay, folks, we've done a huge amount of revision today. We've gone through the whole of the gravitational fields portion of the specification. Hopefully you've enjoyed this video. Thank you very much for watching. Please consider subscribing and liking this video if you have found this useful, and I shall see you in the next one.